Good morning, everyone. This is Samvita, studying second semester of civil engineering in IRE College. Today, I am going to explain about graph structure, learning for early outbreak detection. So, unlocking the hidden connections that drive the spread of diseases, misinformation, and contamination through advanced network analysis from enabled data. And the silent threat, the challenge of early outbreak detection. Rapid spread. Outbreaks, whether diseases, misinformation, or cyber threats, spread through networks at exponential rates, making early detection absolutely crucial for effective intervention. Data limits. Traditional detection methods relied heavily on labeled historical data or predefined network structures, but these resources are often unavailable during emerging threats are in novel situations. The unknown graph problem. How can we detect and respond to anomalies when they are underlying network connections and the relationships driving spread are not fully understood or mapped? So, coming to this, we are here to know about the graph detection or any other things which are helpful for us in the future evaluating technology. So, coming to the topic, introducing graph structure learning GSL. So, what is even when starting with completely enabled data and no prior structural knowledge? So, nodes is something that stores data. So beyond static networks, temporal graphs, the dynamic reality, real world spread is fundamentally dynamic connections which change over time as people move, relationships evolve, and context shifts. Static network models fail to capture this temporal complexity. So, modeling evolution. Temporal graphs model these evolving relationships by incorporating timestamps and dynamic edge weights, creating a more realistic representation of how infections or information propagate. The challenge is that discovering graph structure and identifying infection sources in dynamic networks require fundamentally different algorithms than static approaches. So, in recent advancement, new algorithms and theoretical lower bounds for temporal graph discovery using infection and tracing techniques have been developed to address these challenges. So, learning to control vaccinating strategies, the connection, optimization goal, and research novelty. And the connection. Understanding network structure is fundamental to controlling outbreaks. Knowing who is connected to whom allows us to target interventions strategically rather than randomly. So, optimization goal optimize vaccination strategies to minimize diseases spread by identifying the most influential nodes and connections in the network and research novelty. So, combining graph structure learning with effective vaccination strategies when the graph is now unknown, a previously unexplored intersection of machine learning and epidemiology. So, model uses susceptible infected, susceptible SIS model stimulates realistic disease dynamics where individuals can be infected after recovery. Moving on, unsupervised deep graph structure learning. So, moving beyond supervision, traditional supervised methods require extensive label training data, which limits their applicability to real world scenarios where labels are scarce or expensive to obtain. Unsupervised approaches unlock new possibilities. So, the goal, method, and benefit. Coming to goal, we have to optimize topology using only the data itself without requiring external labels or supervision. And the method Sublime framework uses self-supervised contrastive learning to identify meaningful patterns. And the benefit is that it creates a more robust, adaptable approach that generalizes across different domains and scales. So by learning representations that distinguish between similar and dissimilar node patterns, a Sublime can infer meaningful graph structures without labeled examples. So coming to real world impact and applications. Graph structure learning from enabled data has far reached implications across multiple domains where early detection can save lives. So, epidemiology, early detection of disease outbreaks, including influenza, novel viruses, and emerging pathogens. Rapid identification of transmission patterns enables targeted public health interventions and contaminant strategies. And coming to information networks, identifying the spread of misinformation, fake news, and rumors across social media platforms, understanding propagation patterns and design countermeasures and fact checking strategies. And coming to contamination events, tracing sources of water contamination, environmental pollution, and foodborne illness outbreaks. So, network analysis reveals hidden pathways and helps identify the origin point. And coming to social networks, understanding influence patterns, information cascades, and viral content propagation, business and organizers can optimize marketing strategies while researchers study social dynamics. So, the future, scalable and dynamic discovery. The challenge, real world networks are massive and constantly expanding. Traditional batch processing methods cannot handle the scale and velocity required for real time monitoring. And the solution is that frameworks like Graph FLES enable incremental updates to graph structures as new data arrives, so dramatically reducing computational costs while maintaining accuracy and significance, real-time monitoring and response in complex evolving systems because feasible transforming public health, cybersecurity, and emerging management capabilities. And conclusion is that empowering proactive outbreak response. Powerful tool, hidden connections. So graph structure learning from enabled data represents a powerful new tool for early outbreak detection across diverse domains. And hidden connections. By understanding the hidden connections that drive propagation, we can move from reactive responses to proactive prevention. And future promises that continue research in dynamic and unpreserved GSL promises even more robust, scalable solutions for our increasingly connected world. So the ability to infer network structures from enabled data fundamentally transforms our capacity to detect and respond to threats. As these methods continue to evolve, they will become essential components of public health infrastructure, cybersecurity systems, and emergency response protocols worldwide. Thank you. Imagine trying to stop a wildfire before it spreads. So to do that, you need to know which trees are connected by dry brush. So, but what if the map, the structure of the forest is completely invisible to you? So in many real world scenarios, from disease outbreaks to final fraud, like financial fraud, we are dealing with graph data structures. So we have nodes like people or bank accounts and edges, the connections between them. But the problem, we often don't know where those edges actually are. So today I want to talk about how we learn that hidden graph structure from unlabeled data to detect outliers, those sparks in the data before they run into a blaze. So the problem, the invisible network. Traditional outlier detection often assumes we already have a clean map, but in reality, the connections are latent or hidden. For example, a virus doesn't just spread between neighbors, it spreads through travel patterns we might not see. So, if we guess the graph structure incorrectly, our detection fails. The affected areas might look like random disconnected dots instead of a single growing cluster. So, furthermore, we rarely have labeled data. We might know an outbreak happened, but we don't actually know who was part of it or when it started. So we have to learn the structure and find the outliers simultaneously, using nothing but the raw unlabeled counts at each node. So the solution, graph structural learning. So how do we learn a map from scratch? We use a framework that compares two worlds, the unconstrained world, the graph constrained world. So where we look for the most anomalous blobs of data without any rules is the unconstrained world. And where we force those blobs to be connected by edges is called as a graph, which is constrained world. So by iterating through different possible graph structures, we'll look for the one where the connected anomalies most closely match the raw anomalies. So we are essentially asking what map best explains why these specific nodes are acting weird together. So newer methods even use graph autoencoders, GAEs, that try to reconstruct the graph. So if a node is an outlier, it is so weird that the model can't easily rebuild it, leaving a high reconstruction error that acts as a red flag. So why early days learned graphs detected outbreaks up to 1.7 days earlier than traditional methods. So in a pandemic or a cyber attack, 1.7 days is the difference between a controlled event and a catastrophe. So to wrap up, graph structure learning turns blind detection into informed detection. So by uncovering the hidden relationships in unlabeled data, we don't just see that something is wrong, we see how it is spreading, allowing us to act while there's still time.